Hello, my name is Felipe Arenas-Uribe. I'm from the Universidad de La Sabana in Colombia, and I'm going to present the design and validation of a vehicle data recorder system for testing purposes made in collaboration with Julian Echeverry-Mejia from the Universidad de La Sabana, Contreras from the Tecnológico de Monterrey, and Virgilio Vásquez from the Tecnológico de Monterrey. The motivation and relevance of this work came from the technological advances that are innovating the automotive industry. The new trends, such as the Internet of Things and big data, are migrating the industry towards new technologies that only a small population of the transportation automobiles include. New vehicles have the capability to obtain information and improve the vehicle's performance, the driver's experience, and the utility life of the vehicle by sharing the vehicle's performance data via internet to other devices. Thus, other vehicles that doesn't have internet access are not being part of these technological advances. By developing a device, also known as an in-vehicle data recorder or IVDR, all the vehicles that include the SAE J1962 port will have the capability to capture information of the vehicle's physical variables and transmit it in real time via the internet or record it to an external memory device. The design requirements for the IVDR were established by comparing multiple IVDRs and scanners available in the industry. 12 design requirements were established, but the following are the main ones, which is that it must allow connection between the vehicle's communications protocol, it must integrate a GPS module, the microcontroller used must have validation in the automotive industry, the processing speed must allow no loss of information from the canvas. The IVDR must be programmable, and it must have internet connectivity to allow uploading information to the cloud in real time. To develop the hardware, each of the modules was selected considering the design requirements and having in mind that the final device must allow that an easy must be easy to manufacture and it must be low cost. Mm, Many of the components selected were easy to buy models that are available in many electronic stores. And so the component that needed the most attention was the microcontroller because of the design requirements, and it was selected via a weighting matrix by comparing 8 different microcontrollers that were selected for this comparison because they were either by experience from the others or given that the microcontroller has already been used for a similar device. In general, the IVDR hardware has a GPS module, an SD module, a GPS module for internet access, and has a total cost of $110. The software architecture of the IVDR was made around 4 operating modes. The first one is the sniffer mode, which records all the messages in the canvas. The second one is the IDs mode, which records specific messages from specific IDs. The third one is the OBD2 mode, which records only OBD2 messages. And the fourth one is IDs and OBD2 mode, which records both OBD2 messages from the OBD2 diagnostic protocol and the specific IDs from the IDs select. The IVDR has 4 peripherals, which are the connection to the canvas, the GPS module, the SD module, and the GPRS module. Thus, it was necessary to develop an infrastructure that allowed the 4 peripherals to operate simultaneously without interfering or limiting the operations of others. The solution for this was to develop an interrupt-based state machine that executes the algorithm for the specific peripheral according to a hardware interrupt. The low-level programming of each interruption allowed to give a hierarchy level to each peripheral, thus the system doesn't depend on a sequential or synchronous program, but in a hierarchical interrupt structure. A more in-depth look into the algorithms for each peripheral module is given in the manuscript, including the CAN message reception and interruption, the GPS serial interruption for the GPS, and the GPRS serial interrupt. Also, we included the error handling algorithms implemented to avoid any loss of information. Finally, the validation of the IVDR consisted on comparing its performance to a highly validated, industrially available one, which is the National Instruments NI 9862 model. For this purpose, an acceleration performance test following the SAE J1491 standard was done. In each test, both data acquisition devices were used, following the other requirements from the SIE standard. The similarity between the information acquired from both instruments can be observed in the graph. Given that the two sets of data did not present a normal behavior, a Wilkinson sign rank test was applied to compare the relation between the sets obtained from both devices. The results of the test showed that the mean of the two populations is equal, which proves the relationship between both sets of data. Additionally, to validate there is no data loss in the IVDR, another experiment was made which consisted on 150 trips of 5 kilometers of distance, recording messages from the CAN bus. During the 2,700 minutes of operation, the sampling rate for each ID was compared to the average sampling rate for that ID, considering the standard deviation from the dataset. If the sampling rate for an observation is outside of that range, then it is considered that there is data loss. At the end, the results of the test proved that there is no data loss in the IVDR.